Hi, this is tutorial 8, and it's going to consist of two parts, two big parts actually. So I'm even thinking of recording two tutorials. So this tutorial, what are these parts? The first part is about line or work integrals, work integrals, integrals. This is the first big part. And the second big part is devoted to double integrals, double integrals. But as I said before, both these topics are so big, so serious that I'm thinking of actually recording only the first topic now. And as for double integrals, I think that I'm going to record it in a few days. So these are really serious topics. I need to adjust my image a little bit. Looks much better now. So let's start discussing work or line integrals. So let's write it down as the first topic. First topic 1, work, or some people call them line integrals. Work or line integrals. Let's discuss them. First of all, how do they look like? How can you recognize that you are dealing with the work integral? Work integral looks like ordinary integral, one integral, but you have expression like f times dr. What is here? So this is f is our vector field. It could be 2D or 3D vector field. It's a given field. As for dr, this is the differential of your path. You are going to travel from one point to another point along some line. So c is the line, where c is the path along which you travel. You need to travel in this among these vectors, and you perform some work. The name work comes from physics, because as you know, as I mentioned before, this vector calculus is an instrument which is applied in physics and other fields of science. So this is a work integral. So we can imagine that you are having field. Let it be a 3D field. As usual, I'm denoting the components P, Q, R, and we are in the 3D space. So this path can look something like this. So you travel from point A to point B along some path C, And all this happens in the vector field. So vector field could be imagined like a very big set of vectors. And so as a result, you do some job. Okay, but this is a very short notation for the work integral. What is the expansion? We can easily expand this expression. Let's do it here. So we are given this work integral, which is a dot product. I forgot to mention that this is a scalar or dot product. This is a dot product of two vectors, and it could be expanded. If you remember that f is given here, and dr, by the way, vector dr has coordinates dx, dy, and dz in 3D space, of course. If you are dealing with 2D space, the last component is missing, is omitted. Okay, so if you substitute coordinates of this vector and this vector to this expression and do a scalar multiplication, dot product, so you will have expression like this: p dx plus q dy and plus r dz. So that's how your work integral looks like. Of course, in case of 2D, you will have only the first two terms. The last component will be missing. Okay, so this is the work integral. Now you're pretty familiar, at least you can recognize it. What about circulation? The second term, which we are going to use quite extensively here. Circulation. What is this? Circulation is the work, again, is the work integral, but the path is closed. So C, the path C is closed. This is the only difference. So the integral itself is given with the same expression, everything is the same, but the difference is that you start traveling in point A, and you come back to this point after this, after the journey along this given line. That's it. So, but you know, this case is so important in vector calculus that people even decided to give it a special notation. They put this circle around the sign of integral to highlight the idea that this is not an ordinary work integral, it's just circulation. So circulation is actually a work done along the closed path. This is the only difference. And we are going to deal with both of them simultaneously. Okay, and so the integral looks the same, but the only difference is this notation, just to draw your attention to the fact that this is a circulation, not ordinary work, but just circulation. Okay, so the next question arises. Which types of problems are you going to face? You know, as usual in vector analysis, as you noticed before, we are going to deal with two types of problems. The first one is visualization problems, where you have to deal with drawings, illustrations. And the second type is about calculations. So my suggestion is let's start with visualization problems. They are more exciting probably, and they will give you some intuition. So let's call it part 1A, visualization problems. Visualization. You probably noticed that you are given even two questions in your tutorial sheet 8. These are, I suppose, question 2 and question 3, where you have to solve some problems based on visualization of vector fields. Okay, let's start discussing this. So let's write down our work integral. It's denoted by W, work W. So work integral looks like this. Integral of scalar product of vector field F times dr. And there is some path given here. So what is the main idea behind this visualization approach? The main idea is that you need to recall what is scalar product of two vectors. Scalar or dot product of two vectors. Products. Let's have a closer look at this expression. So F times dr, scalar dot product, according to the definition, it's equal to the magnitude of the first component, the first vector F, times the magnitude or the length of the second vector, and times cosine of alpha, where alpha is the angle between these two vectors. So this is the definition of scalar product. And what are your assignments? What they usually ask you to do? You are given some vector field. If you already looked at these problems, question 2 and question 2, and you are asked to determine the sign of the work integral, the sign of work being done when you travel along some given contour or path inside this field, whether it's positive or negative or maybe equal to 0. So how can we determine it? We should recall this definition, which I just wrote before, and we need to realize that the definition consists of 3 terms. This is the first term, the second term, and the third term. The first term is always maybe non-negative. The second term is non-negative as well. But this guy, cosine, can be either negative or positive or maybe equal to 0. Usually these guys are even actually bigger than 0. They cannot be equal to 0 because you won't be given this task. So the whole idea, the whole answer will be dependent on the sign of this cosine. So what is the main idea? The main idea is that you need to analyze this situation first. Let's draw 3 pictures. I've already spent all the space of the room here. We won't have enough space. Okay, so let's just have a closer look at 3 possible cases. So the first case is when you have dr, maybe horizontally going, And vector F, vector field, is perpendicular, orthogonal to your vector of your path. So dr is the very small vector which shows the direction in which you're moving. So this is the vector of your path, of your direction of your movement. Okay, what if these two vectors are perpendicular to each other? What can you say about alpha? No, alpha, of course, is 90 degrees. And of course, you remember even from school, high school, that cosine of this angle is equal to 0. It means that our work integral, the whole expression will be equal to 0, and correspondingly, the whole integral will be 0, because the integral from taken from 0, 0 will be equal to 0 as well. So in this case, our conclusion will be that the work being done will be equal to 0. So let's highlight it again. So if we are traveling perpendicular to the vector field, in this case, the work done will be equal to 0. Okay, let's consider the second case. So the second case is let vector dr will be the same, going from left to right, and vector f will be like this. So this is going to be our angle. What can you say about this angle? This angle is definitely less than 90 degrees. And this is a very well-known fact that in this case, cosine of this angle will be positive. It means that the whole expression in the definition will be positive, because this term determines the whole sign of this expression. And our work will be positive as well. Okay, and in the remaining case, of course, you can easily figure out what kind of case it's going to be. So dr looks the same way, but vector f looks to the left. It means that the angle between our path direction and our vector field will be more than 90 degrees. In this case, we know that cosine is negative. And correspondingly, our work being done when we travel in this manner will be negative as well. It actually corresponds to the situation when you travel, your direction of your traveling is sort of opposite to the vector field. So that's it. This is the introductory idea. And now it's time to look at some examples. I spend the whole space here. So the first example will be of my own invention, as usual. So let's imagine a very, very easy field, vector field, the easiest ones. So all the vectors are of equal length, and they all go parallel to each other. You're pretty familiar with this field. I introduced this field to you many times before when we were discussing curl and other things. So this is quite the simplest vector field possible. It's like a water flowing in the canal, and the canal is much simpler than, for example, some ordinary natural river, because there are no sources, there are no sinks in the river, no whirlpools, nothing. Just every single particle of water has the same velocity. So, and let's imagine that we are given three paths. So let's imagine this is gonna our first path. So this is A, the start of our journey. This is the end of our journey. So we are travel this way. What can you say about the work in this place, work integral, or just work? Is it going to be positive or negative, or maybe equal to 0? Okay, so we need to realize that this green arrow gives us the direction of our, this is going to be dr, vector dr. And where's our vector field? Vector field goes here. We can, I forgot to put the arrow here. And our vector field goes to the right, something like this. So this is our vector field. And you need to pay attention, special attention at the angle between these two vectors. Remember that you need to have the common origin for the two vectors. Of course, the angle is acute, is less than 90 degrees. In this case, our work is positive. So work is positive in this case. Okay, so it was pretty easy. Let's consider the second example. Let's consider yellow path this time. Let the direction will be the same. This is going to be point R, A, this is point B, and so the whole direction goes in this way. In this case, The yellow vector will be our direction vector. So it looks like dr. So this is our yellow vector. I'm not using yellow because it doesn't look all right, too bright, and at the same time not very legible. Okay, but as for our field vector f, it goes in this direction. So this time our angle is bigger than 90 degrees. It means that cosine is negative, and of course work is negative as well. So, and finally, we just need to consider the last example. When your path from A to B, you travel from A to B, um, lies perpendicular to your vector field. In this case, of course, the work is equal to 0. So as you can see, introductory example was pretty easy. But you know what? The problem is that in your case, of course, no one is going to give you such simple examples. Of course, the vector field will be fancier, much fancier, and the contours themselves will consist of several sections. So, you know what? That is why I decided to give you a little bit more interesting example. Let's call it example 2. The vector field won't be very difficult, but a little bit more interesting than the previous one. So again, like in the previous case, my vectors will be horizontal, but they have a tendency to become smaller as I move downwards along my page. So these vectors in the top row are much bigger than these ones. And again, and these guys are even smaller. So you see the tendency of the vector field now. Okay. So our vector field is a little bit slightly more difficult, only slightly. Okay. So what else? And what is our path? Our path this time consists of several sections. Actually, it consists of several sections. Maybe I should use green. So it starts in point A. Then you travel to the left, parallel to these vectors. This is going to be our point B. Then you travel perpendicular to your vectors to the point C, and after point C you go to point D, which is located just under point A. So your journey, your path consists of 3 sections. It means, according to the properties of the line integral, which we discussed during the lecture, of course, your overall work integral gets split into 3 components. So the work along section AB plus WBC and plus WCD. So you need to evaluate the sign of each component. I think that the middle component, middle term, is the easiest one, because you can see that you're traveling exactly perpendicular to your vector field, and that is why this work is equal to 0. So this is very easy. Okay, let's try and evaluate the first section, the first component here. So you are traveling perpendicular, or not perpendicular, parallel to the vector field, but in the opposite direction. What is the angle phi? Angle phi is equal to 180 degrees. So the cosine is negative in this case. It means that this corresponding component is negative. Okay, nice. Let's switch to the last component, WCD. What can you say in this case? You are traveling parallel to your vector field, and the angle between your direction vector and between your vector field is equal to 0, of course, because this is the same direction. And so cosine of 0 is 1, which is positive. We have very interesting situation here. The first term in this expression is negative. The second, the last is positive. We are not counting this one, of course. And the result depends on whose of these components has a bigger absolute value. Let's have a closer look at the sections now, like through the magnifying glass. What can you see here? I think that in this case, the fact that these vectors are not of the same length really matters. So if you look at this section and at this, if you compare them, you will realize that field vectors are much smaller here, That is why their contribution to the work will be much smaller. So in other words, it means that this work done along the last section will be smaller in terms of absolute value, then this work. So it means that this term will win. So the overall result will be negative. So our work done along this strange contour or this strange path turned out to be negative. And you know what? If sometimes you are asked not to evaluate the work integral, like in this case, but a circulation. What is the difference between circulation? If you were given, if this contour, this path would have been closed, in this case, you will have another section. It will be just called circulation. That's it. No difference at all. So you need to apply the same approach, the same reasoning, but your contour will be just your contour will be closed. By the way, let's evaluate. If you are asked to do circulation, it will consist of four components, four terms, of course. So the first component is the same. So the first three components are the same. I'm just rewriting them here. But the only difference is the last component. So it will be WDA. The last section happens in the same direction. But you know already from the previous result that these three components gave us negative result. And what about the last component? The last component is 0 because we are traveling just exactly orthogonal to our vector field. So the overall result is negative as well, just like in the previous case. Okay, so now after these two small examples, I think you are well prepared to deal with questions which you can find in your tutorial sheet. These are questions 2 and 3. Questions 2 and 3. Vector fields are fancier there, but I don't think it's going to be a big problem for you, to solve these problems. Okay, so we are finished with visualization of line or work integrals, which is the same, line or work integer. And now it's time to start dealing with calculation. On the one hand, it's much easier, but on the other, it's much more time consuming. So let it be part 1b, and it will be called calculation of the line integral, of the work integral, which is the same. So what should you do? So let me remind you that our work integral looks like this: p dx plus q dy plus r dz, and you have letter c here, the usual notation, where c is a path along which you are asked to travel in this vector field PQR. So how can you calculate your integral? What is the technique? It turns out that first of all, there is a general case and there is a special nice case. And to differentiate between, of course, everyone wants to have to deal with a nice case. But determine if you are dealing with a nice case, you need to perform the test. Let's call it let's call it test. You need to check if your curl is equal 0 or no. So curl. Let me remind you that the curl was denoted like nabla vector product F. So you calculate curl, and depending on the result, might have two options, two cases. Let's call them two cases. If nabla F, if your curl is equal to 0, it means that our field is irrotation. Remember this term. It means that you are dealing with a nice case. Nice case. Let's call it nice case. And there is like a shortcut here. I wouldn't call it very short, this shortcut, but nevertheless, it's considered to be better. But if your curl turned out to be non-zero, in this case, you are dealing with a general case. So now you know what we are going to deal with in the next 30 minutes or so. I don't know how much time it will take me. Okay, so we can divide our page into two columns as usual. So what is the nice case? What approach should be used when if you discover that your curl is equal to 0? It turns out that in this case, your result doesn't depend on the structure of this curve. It depends only on the start and end point of your journey. This is a very good result. And on the other hand, this was the second reasoning. The second reasoning is that if your field is rotational, it means that potential function exists. Do you remember this potential function phi? So in this case, in other words, you can calculate your work integral, which looks like this, of course. F times dr along path C. You can just find this potential function phi and calculate its value in the end point of your journey and minus in the start point of your journey. That's it. Looks very, very beautiful. This formula looks really beautiful. But you know what? I think that we need to to make some illustration to illustrate this beautiful approach. So what is the problem? Let's draw some very basic drawing. So you are inside the vector field. So vectors, vectors, vectors here, vectors F here. And you are traveling along some line, which has the start point A and it has the end point B. So you're going from here to here some way. But if this field inside which you're traveling, it turns out to be irrotational, which means that curl is equal to 0, it means that your result, the work done when you travel from A to B, doesn't depend on the form, on the shape of this curve. It could be any curve. It could be parabola. It could be, the segment of the circle, or just anything. That's anything. The result only depends on the final and start result. So it will be phi, this potential function at the end point of your journey, and minus potential function at the beginning of your journey. Also, that's it. So now it's time to go over some example. But you know what? Even though it's called a shortcut, but it's not actually so short, because you need to spend quite a lot of time finding this potential function, as you realized watching the previous tutorial. But you know what? Take it as a good opportunity to go over this technique once again. So what I'm going to do now, I'm going to give you example question 1C from our tutorial sheet. And we are going to solve this problem and discuss many things along the way. Okay, my camera is not very reliable. Okay, so in this question, you are given vector field F with 3 components. So this is a 3D vector field. The first component is 4xyz. The second component is 2x squared z plus 3. And the third component is 2x squared times y. So this is our vector field. And also they ask you to calculate work integral W. But strangely enough, they don't give you the equation of this curve along which you are supposed to travel. Instead, they give you the start point. They say this is the origin. Okay, start point. And they also give you point P with components 2, 2, 3, and this is the end point of your journey. Very suspicious. Why didn't they give us the equation of this curve? So it means that this is a very big hint at the fact that probably this field is just irrotational, and that is why you just don't need to know the shape of this curve. You just need to find this scalar function or potential function, and then to use this shortcut which we just described in our left column. But okay, but nevertheless, even if you are given a problem in this manner, you need to prove to yourself in the first place that this is a rotational field. So this is why let's make step one. Step one, check our curl. Check that this is equal to 0. Okay, so curl is nabla cross f, and this is a determinant. Yjk is the first row. The second row is d over dx, d over dy, d over dz, which is our nabla vector. And the third row, the last row, is pqr. So we need to substitute our data here. P is 2xyz, q is 2x squared z plus 3. Got shifted a little bit. And the last component is 2x squared y. Okay, so Let's calculate this determinant. I'm going to apply the expansion along the first row. So vector I times what? As usual, I'm crossing out the first row and the first column and see what happens. Maybe I should use these pencils. Okay, so what happens? D over dy of this expression, it will be just 2x squared. Nice. Minus, let's have a look at this system again. So d over dz from this expression, it will be over dz 2x squared again. You can see already that the first component is equal to 0, but we should press on. Okay, minus j. So let's cross out the second column and the first row now. D over dx from this expression will be 2xy. And here, 2xy minus 2xy again. Or not 2, 4xy. And finally, we need to finish with the third term, crossing out the third column this time. Try to do it neatly. So d over dx from this expression is 2xz. And the same here. Oh, no, not 2, 4xz. Okay. So it's 4xz minus 4xz. And look at this. All the three components are zeros. I can write it like 0, 0, 0. It means that our field, our vector field f, is rotational. F is irrotational. And it means that we are dealing with this first case in the left column, as I told you before. So let's have a look at this table. So we are dealing with a nice case. We can even write nice case. It's considered to be nice, but it's actually it's quite arguable which is nicer. Both columns will be quite long, to be honest. Okay, this means, and the next step is pretty obvious. We need to find this scalar or potential function, and after this, use this really wonderful, beautiful formula. Okay, let's do second step. Find our potential. Find potential phi. Find potential function phi. We need to refresh this technique because last time it seemed to be like a challenge, quite a big and challenging problem. Okay, so let's have a look at our assignment again. So we have these three components, P, Q, and R. In the case of a rotational field or potential field, it has different names. These guys are actually partial derivatives of our function phi. So the first component, P, is usually d phi over dx. The second component is d phi over dy, and so on. So let's rewrite this like our given information. So d phi over dx is given to us, is actually equal to the first component P, which is 4xz, xyz. The second component, we usually denote it as q, but in this case, it will be d phi over dy. So we just rewriting, copying it here, 2x squared z plus 3. And the last component is actually d phi over dz, which is 2x squared y. 2x squared y. So this is the given information, and our task is to find this function phi, which has these three partial derivatives. And let's remember our technique, not technique, even algorithm. I would call it algorithm. So the first step, we need to use all these three pieces of information in turn. So let's use let's use the first piece of information. So we can integrate this expression by x, and then it will be the first step in finding our function phi. So I'm not going to write as much as last time, because I'm not explaining it to you anymore. I'm just reminding you of this technique. So we need to integrate this expression with respect to x. In this case, all the remaining variables except for x turn into constants. And that is why we have 4yz like a coefficient. And the antiderivative will be x squared divided by 2. But the interesting thing is that we need to remember about this constant of integration, which is not constant in our case. It's a function depending on which variable. You just integrate it with respect to x. That is why remaining variables should be written here. I think it's better to rewrite it because I'm tempted to cancel out these guys, 4 and 2, to simplify them. So it will be 2 yz times x squared plus this function c1 of yz. So this was our very first step. Okay, and it means that we already used this piece of information, the first piece of information. Okay, let's move to the second expression. How can we use it? So we actually found partly found our function phi. This is function phi, not finished yet. We can find the derivative according to the formula with respect to y, and then set it equal to this expression. So let's find derivative d phi over dy from this expression. So we need to rack our brains. We need to be concentrated now. We are going to take derivative with respect to y. It means that only y is a value here. 2zx squared remain unchanged. They turn into constant. 2zx squared, and this is going to be y squared divided by 2. And when you take derivative from this guy, you need to write it in this way: dc1 over dy of yz. Looks pretty fancy, but it's not a big problem. Okay, so we did the left-hand side of this equation, and we need to set it up to the right-hand side. And now we need to have a closer look at this expression. Look at this. These two guys, this and this, they are actually equal to each other. So we can cross them out. They cancel each other. And so we have this expression. We have these equations that dc1 over dy of yz is equal to 3. How can we find c1 now? Oh, very easy. C1 actually is so we are going to integrate it with respect to y. It means that we'll be left with only one variable, z. Instead of 2, y and z, you will be left only with z. And so we need to take the integral from this expression over with respect to y. Of course, integral is very super easy. It's 3y plus c2, by the way. But c2 is dependent on which variable? C2 is dependent on, I think, yz. Oh, no. Yz. Oh, no. I should have written yz. Sorry. It will happen. The elimination, the disappearance of y will happen later. Okay. So I just integrated with respect to y. It means that the remaining variable is dependent on z. Oh, no, it wasn't a mistake actually, but okay. It looks a bit maybe scary. Okay. So now I can get back to my expression for phi, which was framed. And now I can rewrite it more neatly. So my phi was this term from there, 2yzx squared. And instead of c1, still c1 should be written like this, of course. Sorry for this mess. So c1 should be written like this. Instead of c1, we can write this, 3y plus c2 of z. And again, we can say that we already used the second piece of information. And finally, the time comes for the last piece of information. How can we use it? We can say to ourselves, it looks a bit blurry at times. I don't know what's the problem. I need to change my pencil, by the way. Okay, so we almost finished. Look at this. Our file looks pretty nice already, with the exception of this term. And of course, at the same time, we can realize that we haven't used the last piece of information. How can we use it? Just like in the previous step, we need to calculate derivative of our function with respect to z. Let's do it first. What is the derivative of this expression with respect to z? It will be 2y x squared from the first term. From here we'll get 0, and from here we have like dc2 over dz. Okay, so I calculated the left-hand side of this expression, and I need to set it equal to the right-hand side, 2x squared y. And again, this is a very nice expression, actually, nice equation. Look at this. These two guys get cancelled out, and we end up having the derivative of c2 over dz is equal to 0. It means that c2 itself, c2 of z, is equal to integral from this expression, which is 0. And of course, it will be 0. 0 plus, I don't know, plus maybe c3. Okay, so we can substitute. Finally, we can write our phi finally. So we're rewriting all this expression here, squared plus 3y. And instead of C2 of z, we can put just C3. If you don't quite like this C3, you can easily denote it back just like C. It's just a convention, mathematical convention. Okay, so it wasn't so bad. If you practice this algorithm quite a few times, you will be amazed how quickly it can be calculated. It's all the matter of practice, matter of training. But you know what? After test 1, you realize that it's always nice to have some technique to check your results, because it's pretty obvious that I could have done many careless mistakes here. How can I check my result? Checking is super important, as you realized. Okay, let's discuss checking. Some people might get impatient. They might say, "Oh no, it's better to solve this problem as quickly as possible." But it's not a good idea. It's not always good. It's never good to be in a hurry. So how can we check our result? We can find all the 3 partial derivatives and compare them with our given PQR. They should be equal. So this is a nice, actually, situation that we can check ourselves. So let's find all these 3 partial derivatives. So d phi over dx, it will be 4yzx, if I'm not mistaken, and plus 0, I'm not writing them down. Okay, where's my second derivative, d phi over dy? From the first term, it will be 2zx squared plus 3. And the last derivative, d phi over dz, is equal to 2yx squared plus 0, and I'm not going to write this. And now it's time to compare these expressions, these 3 derivatives, with our data. Look at this. So d phi over dx should be equal to p. Yeah, they are equal to each other. Nice. The second derivative, d phi over dx, should be equal to q. Look at this. They are the same. And finally, comparing the last 3 components, they're same as well. It means that our result is absolutely correct. It's 100% correct, I would say. So that is why we can proceed further. So what was the assignment? Let's call it step 3. What was the assignment? What was the assignment in this question 1c? The assignment was to find the work integral. Do you remember? We needed to find the work integral from when we travel in this vector field from point 0 to point P, or not point 0, point O from point P. But we know that our work integral, we don't even need to write this work integral. All we need to do, we need to calculate our potential function phi in the final point, which is P, and minus in the point 0. Minus in point 0. That's all. So it all comes down to all these calculations. But to do this, I think it's better to copy my function phi here. So my function is 2yzx squared plus 3y plus c3. And we can use this notation from 0 to p. 0, not 0. Origin has coordinates 0, 0, 0. And final point P have coordinates, I don't remember them, 2, 2, 3. 2, 2, 3. So that's what we need to do. So this notation means that first you need to substitute these components into this equation, which is going to be phi of P. And then minus and substitute in this expression. Okay, let's substitute 2, 2, 3 instead of x, y, and z. So 2 times 2 times 3 times 2 squared plus 3 times 2 plus c3. So I substituted this point P here. And if I substitute components of the origin, the first 2 terms will turn into zeros, and I will be left only with this last term, which is C3. So C3 and 3 gets cancelled out. And what do we have here? It will be 12, it will be 48 plus 6. So my result is 54. My answer in this problem is 54. As you can see, it's considered to be a shortcut, but in reality, it's not so short. I wouldn't call this shortcut very short, play on words, because they know in part is that you need to find your potential function first, which is pretty annoying if you don't have enough experience. So this is why my recommendation to you is to solve, like, I don't know, maybe 2 or 3, maybe even 4 similar problems of finding a potential function. And only after that you will feel more or less confident when it comes to calculations like this. Okay, so this was the nice case, nice case as to how to calculate these work integrals. So what about the general case? What about the general case? I'm thinking about circulation. No, I'm not going to go with circulation. Let's get back to our table. Look at this. So we had our table here, which says that if the curl was equal to 0, go to the left table. Use this shortcut, this which we called a nice case. But what if your field is irrotational, not irrotational, which means that curl is not equal to 0? What is the general case? What is the general approach to calculating line integrals? So let's call it general case. General case now. General case. This was nice case. And what techniques are used for general case? You know what? I think that we need to draw another table. Let's draw another table, another little table, because it's always a good idea to organize all your information in one table. So I'm going to write this title again: general case. General case. General case about what? About calculating work integrals. So FDR, or maybe even circulation FDR. Do you remember circulation has a different, has a special notation? This is the circle in the middle of this integral sign. And C and C. C is the number of the contour of your path. So you perform this test about curl, and you realize that you are not dealing with the irrotational field. So you need this general technique. And so how this general technique could be described? Let's consider 2 separate cases. Let's divide my page into 2 columns again, as usual. So the first column will be devoted to 2D case, and the second column will be about the 3D case. In the 2D case, your work integral will look, if you expand it, p dx plus q dy. And this is the name of your path. We can even expand it. We can even write this expression in more detail. Let us just let me remind you that these PQ are not numbers; they are functions. They are functions of 2 variables in this case: p of x y dx plus q of xy dy, and this is the name of our curve. And we can even make a little drawing. So you are dealing with 2D case, which means that you are on Cartesian x, y, z plane, and your curve looks like this. Your curve, and you are given direction of travel along your curve. So how can you deal with this situation? How can you calculate this very strange looking integral? So it all depends how your path is given, in which form your path is given, because this is a typical graph on a Cartesian plane. And you know that there are several methods of giving, the equation of your path. The first case is then when your path is given in the form of function y of x, y of x, y of x. In this case, you can, of course, you are given some segment of this path, and this is why you could use these letters A and B denoting the start point of your journey and the end point of journey. And let's call A, the components A as XA and YA, and the finishing point, let it has components XB and YB. So how can you calculate your integral in this case? The idea is very simple. In this case, so let me write the integral here. So integral looks like this: p of xy dx plus q of xy dy. So what is the approach? You know what? The problem with this integral, why does it look so scary? The problem is that it has 2 letters. We can't calculate integrals with 2 letters, x and y, 2 variables. What can we do? It turns out the technique is very, very simple. It's laughably simple. To get rid of this letter, annoying letter y, for example, you can see it in three times. You can substitute this expression instead of this letter. That's it. So instead of y, you substitute y of x, your formula here. Here you substitute y of x, and also here you substitute this expression, this formula for y of x, wherever you see this y. That's it. This is the whole technique. The whole technique. So let's put aside this table, and let's consider some examples, some concrete example. I'm looking for my examples. I prepared them somewhere, but now I can't find them quickly. Yeah. I can see example. Okay, so this is going to be example of my own invention, not from any tutorial sheets, just of my own invention. I still can't find it. Yeah, it's here. So you are asked to calculate the integral x squared y dx plus x y squared dy, and where past c is given by formula y is equal to x squared. You probably immediately recognize parabola, and the start point is origin, and the end point is point A with coordinates 2 and 4. So this is whole information which is given to you. Okay, so what is your first move? What should you do in the first place when you encounter this problem? You know what? It's better to check for the nice case, of course, because of course I'm going to tell you about how to deal with the general case now. This is the purpose, the whole purpose of this example. But nevertheless, it's always a good idea to check this field for curl being equal to 0, because in this case you won't need to this technique at all. So let's make this test. By the way, maybe you remember long ago, maybe not long ago, maybe 2 weeks ago, I told you the shortcut for checking the curl. Instead of instead of calculating the whole curl, if it's equal to 0, the whole curl, calculating the curl of your field is quite a long story, because you need to write down this determinant, I, J, K, and so on and so on. But in 2D case, instead of checking the whole curl, you can check this small equation. So dp over dy should be equal to dq over dx. If you remember this technique, it will be very nice. It will be very helpful to you. So if this this equation is true, it means that your field is rotation. Let's check this. So our p is this component p dx, and this is our q. So this is our vector field. Let's check. So let's write them down here. P is equal to x squared y, q is equal to x y squared, and let's check this derivative. So dp over dy is equal to x squared, and dq over dx is equal to y squared. No, they are not equal to each other. It means that our field is not irrotational, and that is why phi doesn't exist, and it means that no option for us is to learn this new technique. But as I described before in this left column of our table, this technique is super easy. So all you need, let me write this integral here again. X y dx plus x y squared dy. All you need to do, you need to realize that you have this annoying letter y, which is here, and here. And all you need to do, you need to substitute this y with this expression, because y is equal to x squared. So let's just do it. I don't know, maybe it's better to do it here. So x squared, and instead of y, I'm writing x squared again, because that's what y is equal to 2. dx gets rewritten x. Now I need to substitute something instead of y, x squared, and it was squared as well. D and d of x squared as well. You can substitute everything even in the inside the differential, and that's it. And a miracle happens immediately. Look at this. Even though this integral still looks a bit messy, but we achieved our main objective. We did get rid of the second variable. Now we have only x's, everyone here. Okay, so it's time to clean up this a little bit. So this guy will be x to the power 4 dx. This will be x to the power of 5 d of x squared. So now it looks much better. But you know what? Uh, Along the way, we can we can realize that we are dealing with the ordinary integral already, almost. We haven't simplified it correctly yet. But what about the limits of integration? Limits of integration could be seen from here, you know. So these components, the first components are x's, and that is why from 0 to 2, you can write immediately that our integration will happen from 0 to 2. Okay, but what about this strange term? How can we calculate this thing? Let me remind you that to calculate differential of some function f of x, for example, so you have a function f inside your differential, you need to calculate the derivative of the function and then to multiply it by dx. So let's apply this to this expression. So I'm rewriting the first component, the first term. And as for this term, what I'm going to do, d of x squared is the derivative of x squared, which is 2x, and times dx. So I can even highlight it for you. So this differential corresponds to this differential here. So that's how we got rid of this strange situation. Okay, now it's time to do further simplifications. So let's rewrite the first term again. So it's going to be, no. Now we can notice that these terms actually have one common factor, dx. So we can pull out dx, but place it not in the beginning, but in the end of our expression. So the first term will be x to the power of 4. The second term is 2x to the power of 6. And dx has been pulled out. So, and now it turned out into ordinary integral. Let's integrate it. So the integral from the first term will be x squared, x to the power of 5 divided by 5, and limits from 0 to 5. And as for the second term, it will be 2x to the power of 7 divided by 7 from 0 to 2. And finally, we have 2 to the power of 5 divided by 5 minus 0. I'm not writing it down. Plus 2x to the power of 7 divided by 7 minus 0, and is equal to so on. I'm not going to finish my calculations. It's too boring, I think, for everyone. So as you can see, this is a super easy technique actually to general case. Maybe general case looks even more appealing in some cases. But don't be tempted to use general case all the time, because in many cases, more often than not, it may lead to very difficult integral. And that is why it's recommended to use this technique instead. These integrals which you come across when calculating this potential function are much easier than these integrals, by the way. So don't be tempted. It's not for nothing that they gave you this, nice case, so-called nice case, short case in your course, because it's really much better. Okay, so let's get back to our table. So this is a table where I collected all the possible technique. So for some mysterious reason, I denoted as the first technique. So what is the second technique? It turns out the problem is that sometimes you are given your path C in a different form, especially the special case is a circle. So you remember the equation of the circle, x squared plus y squared is equal to r squared. In this case, if you try to use this technique, which we have already just mastered, it will lead to very, very ugly and very difficult integrals, because if you express y in terms of the remaining variables here, you will end up having a square root of some fancy expressions, and integrals from square root are not nice at all. They can be super difficult to calculate actually. So what can you do in the case of circle? In the case of circle, it's recommended to use a quite different equation of this circle. This looks nice, but it's not nice for integration. It's recommended to rewrite this equation in a parametric form. So the parametric form of the circle is r, radius r, times cosine of t, and y is equal to r times sine of t. And as you can see, maybe these expressions are pretty familiar to you. They they actually look like polar coordinates, and it's quite true. So this t plays the role of this polar angle, and that is why if your path is the whole circle, so you can easily say that your angle changes from 0 to 2 pi, the whole circle. So, so these things should be sort of memorized or just written to your cheat sheet, actually, for the exam, maybe for your next test, and so on. So every time you have to deal with the circle, remember that it's better to rewrite it in a parametric form. So instead of x and y, you write these expressions, and then you treat t as an angle, as the polar angle or trigonometrical angle or whatever it's called. So this is much better. Integrals will be much easier. Okay, so now it's time to apply this technique, of course. Let's have a look at the example when you have to deal with this circle. When you're asked to calculate some work integral or maybe circulation, but you're given circle, you pass this circle. Okay, so this is a question, actually question 4a. Question 4a from our tutorial sheet. So in this question, you are given a vector field F with components, very easy components, y and minus x. Only two components, but your path is x squared plus y squared is equal to 4. And you are asked to calculate circulation. Circulation. So this is our assignment. Of course, you realize that circulation is a work done along the closed path. So when they write the equation of the circle to you, they mean the whole circle. The whole circle, which means that our angle will be changing from 0 to 2 pi. Okay, so now you know the technique. If we are dealing with this circle, we need to rewrite it in a parametric form. In our case, it will be r. Radius is 2, of course, because this guy is 2 squared, radius squared. So 2 cosine of t, y will be written as 2 sine of t. And these are going to be our expressions for x and y. And t is an angle, and as we are dealing with the circulation, they mean the whole circle. So travel along do the whole circle from 0 to 2 pi. Okay, so, and now we need to write this integral. So our circulation will be given with the same integral, f dot product dr along the bus c, but we should put the circle around here to symbolize that we are calculating the circulation. Okay, what next? Now we need to rewrite it as p dx plus q dy. As you can see, we are dealing with 2D field, luckily, 2D field, so only two components. Now let's substitute our concrete data, so it's y dx minus x dy. And that's it. But you know what? Maybe in a real situation, of course, you need to check that your field is not is rotational, because in the case when it's rotational, the things might be much easier, you know. But let's do it further. I know for sure that circulation, that rotation curl is not equal to 0, so we need to use this general case. Okay, so what do we need to do? The things are very easy. Instead of x, wherever you see x, we see x here and x here. You need to substitute this expression for x. And wherever you see y, and you see y in two locations, you need to substitute it with this expression. That's it. And you will end up having only one letter under your integral. Not two letters, x and y, but only one letter t, only one variable, I should say. Okay, so instead of y, I'm substituting 2 sine of t d, and instead of x, I'm substituting 2 cosine of t. It looks very strange, but I don't care about it. Minus x. Instead of x, again, I'm substituting 2 cosine of t, d of what? 2 sine of t. And now we do have only one variable, one letter. It means that it's time to think about limits of integration, which are from 0 to 2 pi. And now it's time to simplify this expression a little bit. Okay, so what I'm doing, I'm rewriting 2 sine of t, but I'm calculating this differential by taking derivative. Derivative of cosine is minus sine, sinus t, so it will be minus sine 2 sine of t dt. And of course, I'm highlighting these special places. So this derivative, the derivative differential is equal to this expression. Now, what about the next term? This guy gets rewritten, and the derivative for sinus is cosinus. So it's 2 cosine of t dt. And again, it's better to highlight it. So this was differential, and it's equal to this expression, to this differential. Okay, so now what do we have now? We can pull out dt out of these two big terms, the first term and the second term, the red term and the yellow term. And also we can do some simplification along the way. So the whole the first term will be minus 4 sine squared of t. The second term will be minus 4 cosine squared of t, and dt is pulled out. But you know, this expression looks very beautiful, and we can pull out minus 4 out of this expression. And moreover, we can even pull it out of the integral, this coefficient minus 4. Let's do it. So minus 4 gets ahead of the integral. And then the integral, you have this beautiful, beautiful expression, dt. And you're supposed to recognize it immediately because according to it's one of the most famous formulas from trigonometry, is equal to 1. So our integral essentially is integral of 1. So mathematicians are even lazy, they don't write this 1, they just write something like integral over dt. But in any case, it's just t with limits from 0 to 2 pi. So it should be calculated as 2 pi minus 0. And the answer will be minus 8 pi. So that's it. That's it. Our answer is minus 8 pi. So as you can see, let's get back to our column. So in case of 2D, you might have with two situations, depending on which in which form your curve is given, your path is given. If it's in a Cartesian form, then you need just to substitute y with your expression, with your formula. But if you're dealing with the circle, the best recommendation is to use this parametric form, because otherwise you will have big trouble with integration. Okay, but what about the case 3D? Let's discuss the case 3D. I haven't found an example devoted to 3D case in your tutorial sheet. So I concluded that you might not need to know how to deal with this case. But nevertheless, I think it's a good idea to write it down here. So in this case, your integral, your work integral will look like this: p dx plus q dr dy and plus r dz, and some curve c. In this case, there is only one option here. If your curve is in 3D space, it can be even drawn something like this. So this is your curve in 3D space. It turns out that the best way to define the curve in 3D space is to write it in a parametric form. So this is the best case. So you need to rewrite your curve in the parametric form, or maybe it will be given already in the parametric form. And then you know the technique. Wherever you see letter x, you need to substitute it with this expression. Wherever you see letter y, you need to substitute it with this expression, and so on and so on. And of course, you need to realize that your t is changing from some start point to some end point. So this is the general technique, pretty similar to these techniques at all. So it all looks like your purpose when you start calculating work integral, or maybe calculate circulation, which is just a particular case. The whole objective is to get rid of many variables. Your whole objective is to be left with one variable, one letter only. And the last thing which I forgot to discuss with you is, so in case of work integral, you have this general case and you have a nice case. Nice case happens when your rotation is equal to 0. In this case, you can find potential function phi and use this beautiful formula. But what about circulation? Let's wind up with circulation. Let's look at the circulation once again. Are there any nice cases there, or you should always use this general technique? No, it turns out that, again, if you're dealing with circulation, then you're asked to calculate this integral. with this circulation. Or maybe you need to check curl first. Check curl first. And you will end up with two options. So two cases. The first case happens where if your curl is equal to zero, it means that your result, your integral, doesn't depend on the shape of the curve, which links the start and the end point. It depends only the final and start results. But you know what? If you're in this case, if you're dealing with the circulation, your curve is closed, and that is why your start point coincides with this finish point. It means that phi of B is equal to phi of A, and that is why phi of B minus phi of A is just equal to 0. So it means that your integral is just equal to 0. This is a very fine, very beautiful result. So please try not to miss this beautiful case, because sometimes it happens so that people are asked to calculate the circulation of a very serious integral, very serious field, and they start dealing with this general case. But when in reality, they should have checked the curl, and if the curl turns out to be 0, you actually don't have to do anything at all. You need to give the answer 0. That's it. Just imagine. But if this is a general case, of course, you need to do you need to apply a lot of effort, of course. Then general case. So this will be general case. You need to look to have a closer look at your curve, and so on and so on. So okay, as I said, this is not the whole tutorial 8. It's only the part of tutorial 8. I covered all the questions except for the last one. And the last one, even though it looks so small and insignificant, but actually it encapsulates the big topic, which is called double integrals. And so this is going to be the topic of my second tutorial. It will be called tutorial 8 again, but maybe like part 2 or something like this. So it's such a big topic that I decided to record it separately, maybe tomorrow, maybe the day after tomorrow. So that's it. Bye-bye.